Hello students. Some sound issues were reported in the alternate derivation for the Boltzmann distribution by the method of most probable distribution, part 1 of the video. So I think from some 17 minutes onwards there was some issues with the sound, and thereafter towards the end of the video there was no audio at all. So let me resume the lecture from almost 17 minutes. So I will be repeating the lectures from 17 minutes. So just watch up to 17th minute in the previous video, and you can continue with this one. So what we were talking about, we were talking about the distribution of systems in the ensemble, which consists of total n number of systems. Okay, so we have seen that the n1 out of n systems are in state 1 with energy E1. So this is the way in which we are taken. N2 systems out of n systems are in state 2 with energy E2. N3 systems out of these systems are out of n systems are in state with energy E3, and so on. So that was the thing. And finally we have assumed that NR systems out of total n number of systems are in a state R with energy ER. So we can see that the set of numbers n1, n2, n3 etc. up to nr, which I am representing as set nr, where r equal to 1, 2, 3 etc. That must satisfy the conditions. So what is the condition that should be satisfied by set of number nr? You know, as per our assumption, n1, n2, n3 etc. up to nr are from total number of systems en. So we can say that the first condition will be that sum over r nr should be equal to the total number of systems in the ensemble en. I am using the curly letter n, which denotes the total number of systems in the ensemble. Okay, so what does it mean? Actually, what does it mean? It means just that n1, that is n1 plus n2 plus, okay, so n1 plus n2 plus n3 plus etc. right? Okay, up to nr, whatever it is. Suppose that there are r number of systems, so that should be equal to what? The total number of systems in the ensemble. That is only meaning of that. Okay, and that is correct as per equation number 1. So we call this particular condition, so this is actually acting like a constraint, right? So this particular condition I'm calling it as 2a. Let me call it as 2a. There is one more condition. What is the condition? N systems are sharing a total energy of E, right? N systems are sharing a total energy of E. How it is sharing? That is, N1 systems out of N systems are having energy E1. N2 systems out of N systems are having energy E2, and so on. Okay, so we can say that the second constraint will be put together. Okay, so you just sum all the energy of the systems in the ensemble. That will be equal to sum over R. I can write it simply as NR into ER. Okay, NR into ER should be equal to what? The total energy that is shared by the systems in the ensemble, right? So this is nothing but I can call this equation as equation 2b. I'm calling this equation as 2b. What is it meaning? It means that N1 into E1. From where? From equation number 1. We have N1 systems in state 1 with what? Energy E1. So what will be the total energy of these N1 systems? It will be N1 into E1 plus, what is that? Plus, I can say N2 into E2. What is N2 into E2? Because there are N2 systems which are having what? Energy E2. It is in the second state. Okay, so plus N2 E2 plus N3 E3 plus etc. up to what? I can write NR into ER. That should be equal to what? The total energy that is shared by all systems in the ensemble, which we have called represented as what? E. So this is the thing. So these two constraint equations are very relevant. So see that you note it down. Equation number 2a denotes the constraint in terms of the total number of particles, and equation number 2b not number of particles, number of systems in the ensemble, and equation 2b denotes the way in which energy is divided, okay, between the members of the ensemble. Okay, here one thing what I have to mention. So here, let me continue. Here we can just say that this total energy E can be written as N into U, where U is equal to E by N as per the definition. Okay, that is nothing but the average energy per system of the ensemble. Average energy per system of the ensemble. So U is defined as the average energy per system of the ensemble. And 1 minute, okay, you have to think of why should we discuss about the average energy per system of the ensemble. The reason is that, you know, we are discussing a canonical ensemble where the energy of the system is permitted to vary. Actually, it's instead of energy, the temperature of the systems are kept to be a constant. So energy of the system in principle can vary from 0 to say an energy E, right? So we can assume that systems in the ensemble will be having all possible values of energy. Okay, systems in the ensemble will be having all possible values of energy. So due to that reason, we have to define what is known as average energy. You know, you define average of any quantity whenever that quantity is undergoing a variation. Okay, so that is why we are defining average energy of the system in the ensemble beforehand. So remember, this equation will be using later. Okay, let me call this equation some C, okay, for the time being. Okay, so you keep it now. So what we have done so far, we have seen that equation number 1 is the way of distributing systems, okay, systems with particular energies, right? And the set of these numbers n1, n2, etc. up to nr, which we have represented as what? Nr, set nr, that should be satisfying conditions 2a and 2b, right? Now we can say that in principle the total energy can be distributed in a large number of ways, right? Means the value of n1, n2, n3, n4, nr, it can be having a lot of possibilities. നമ്മൾ ഈ കാണുന്ന സെറ്റ് എൻ ആർ എന്ന് പറയുന്നതിനകത്ത് n1, n2, n3, etc. എന്ന് പറയുന്നത് പല രീതിയിൽ വേരിയേഷന് വിധേയമാകും. ഉദാഹരണത്തിന് സപ്പോസ് ദാറ്റ് okay, no, just it's like 1, okay, 2, 3, 5, 7, etc. Okay, ഇപ്പോൾ ടോട്ടൽ എത്രയാവണമെന്നേ ഉള്ളൂ. സോ ടോട്ടൽ ആവുന്ന എത്രയാണ്? സപ്പോസ് ദാറ്റ് I have only 5 systems. I have only 5 systems. Means suppose that I am just taking a very simple toy model. Don't okay, expect this toy model to be correct. So suppose that n is equal to 5. Okay, n equal to 5 means there are only 5 systems in the ensemble. Okay, so let me say that the number of okay, you can, not 5 systems. You can see that it will be the, what will be the number of systems here? 1 plus 2, 3, 3 plus 3, 6, 6 plus 5, 11, 11 plus 7, 18. So means there are altogether 18 systems in the ensemble. Okay, and suppose that it is sharing some 100 joules of energy or 100 electron volt of energy is shared amongst 18 systems of the ensemble, right? So one possibility is that one system is sharing say that 1 joule, okay, and 2 systems are sharing the 3 joules each. So 3 systems are sharing say 10 joules each. So now you have to calculate how much energy it is already shared. ബാക്കിയുള്ള എനർജി 5 സിസ്റ്റവും 7 സിസ്റ്റവും തുല്യമായിട്ട് ഡിവൈഡ് ചെയ്യുന്നു കരുതുക. അപ്പോൾ നിങ്ങൾക്ക് ഇവിടെ കാണാൻ പറ്റുന്ന ഇതാണ്, ഇതൊരു ഡിസ്ട്രിബ്യൂഷനാണ്. ഇപ്പോൾ ടോട്ടൽ നമ്പർ 18 ആവണം. ഈ ടോട്ടൽ നമ്പറും ടോട്ടൽ എനർജിയും കൺസേർവ്ഡ് ആവുന്ന രീതിയിൽ ഈ എണ്ണം ഇനി മാറ്റാം. ഉദാഹരണത്തിന് ഇത് 1, 2 ആവാം. ഇവിടെ 3 വന്നതിന് പകരം ഇതെന്താവാം? 4 ആവാം. ഈ 5 അപ്പോൾ എന്ത് ചെയ്യുക? കുറയുക. 5 4 ആയാൽ മതിയാവും. ആൻഡ് ദിസ് ഇസ് 7. ഓക്കെ, അപ്പോൾ ഇതിൽ നോക്കുക, ഇതിൻ്റെ സം എന്ന് പറയുന്നത് എപ്പോഴും വീണ്ടും എത്രയാണ്? 18 തന്നെയാണ്. അപ്പോൾ എനർജിയിലും ഒരു ഷെയറിങ്ങിലും വ്യത്യാസം ഉണ്ടാവും. അതായത് ഈ എൻസംബിളിൽ ഉള്ള ടോട്ടൽ എനർജി എന്ന് പറയുന്നത് വ്യത്യസ്ത രീതിയിൽ അതിൻ്റെ മെമ്പേഴ്സിൻ്റെ ഇടയ്ക്ക് ഷെയർ ചെയ്യാൻ പറ്റും. ഓക്കെ, അപ്പോൾ പക്ഷേ ഷെയർ ചെയ്യുമ്പോൾ ഒരേ ഒരു കണ്ടീഷനേ ഉള്ളൂ. ഇക്വേഷൻ നമ്പർ 2aയും ഇക്വേഷൻ നമ്പർ 2bയും ഒബേഡ് ആവുന്ന രീതിയിൽ ഏതൊരു വിധ ഷെയറിങ്ങും പെർമിറ്റഡ് ആണ്. അപ്പോൾ അത്തരത്തിൽ നടക്കുന്ന ഷെയറിങ്ങുകളിലെ n1, n2, n3, etc. nr വാല്യൂസിൻ്റെ സെറ്റിനെയാണ് നമ്മൾ സെറ്റ് nr എന്ന് വിളിച്ചിരിക്കുന്നത്. ഓക്കെ, അപ്പോൾ ഇൻ പ്രിൻസിപ്പിൾ പറയാൻ പറ്റും any set of nr which satisfies condition 2a and 2b is a possible mode of distribution. Any set nr, so that is our conclusion now. Any set nr, okay, which satisfies ഒറ്റ കണ്ടീഷൻ ഉള്ളൂ, ഏത് സെറ്റും ആവാം, പക്ഷേ അതെന്ത് ചെയ്യണം? it should satisfies equations, constraint equations 2a and 2b, constraint equation 2a and 2b, okay, is a possible distribution. ഇതൊരു possible distribution ആണെന്ന് നമ്മൾ പറയുന്നുള്ളൂ. is a possible distribution. Possible distribution of what? possible distribution of total energy E among how many? Total energy E among n members of the ensemble. Among n members of the ensemble. Among n members of the ensemble. Right? Okay. Now, see, any such mode, I can call it as a mode of distribution. Any such mode of distribution can occur in a large number of ways. Okay, so the number of ways in which such a distribution can occur. Which distribution? A distribution that satisfies what? Constraints 2a and 2b is given by. So in order to get the number of ways in which such a distribution can occur, we are defining what is known as a weight factor is given by the weight factor. Is given by the weight factor. I am defining the weight factor like this. See, W corresponding to a particular set NR. So we are writing it as W of NR. It's not W into NR. Remember, this NR is written as a subscript. Okay, so it is just W corresponding to a given set of NR. WNR, that's equal to, see, this is an equation that we are borrowing from, say, permutation theory or combinatorics theory. So n factorial divided by n1 factorial into n2 factorial, etc. up to nr factorial, like that, if it is running up to r, right? So we call this equation as equation number 3. See, what is this equation number 3 representing? It represents the number of ways in which a set nr can occur, which satisfies the condition 2a and 2b, right? And remember, see, don't worry from where such an equation has come up. This equation has come up from the basic theory of permutations. For example, this equation represents the permutation, number of permutations of, number of meaningful arrangements of n things. Okay, so this represents the permutation of, I can say, permutation of, remember this is the theory that we are borrowing, permutation of n things, it can be different things, in things, out of which n1 are alike, n2 are alike, n3 are alike, etc. It means, for example, okay, I had cited an example previously. Suppose that you have got some, say, some 10 balls are there, right? Okay, any number of balls, say that. Okay, and you are going to calculate the number of permutations of these balls, right? So let's say that, so this is this, 10 is nothing but the total number here. Now, let me say that these 10 balls are of 3 types. They belong to 3 types. See, say that some, 4 of them are red. 4 of them are red in color. Okay, 3 of them are blue in color. So it's 4 plus 3, 7, and the remaining 3 are green in color, right? So that is the way in which, 4 are alike, 3 are alike, and 3 are alike. It's just like n1 are alike, n2 are alike. In what way n1 are alike? Because n1 systems out of n systems are having same energy, E1. That is how n1 systems are alike. n2 systems all are having what? Energy E2. So that is where they are alike. അതുപോലെ തന്നെ ഈ 10 ബോളുകളിൽ 4 ബോളുകൾ റെഡും 3 ബോളുകൾ ബ്ലൂവും ബാക്കിയുള്ള 3 ബോളുകൾ ഗ്രീനും ആണെങ്കിൽ ഈ 10 ബോളുകളെ വെച്ച് ഉണ്ടാക്കാവുന്ന മീനിങ്ഫുൾ പെർമ്യൂട്ടേഷൻസ് എന്ന് പറയുന്നത് that will be equal to, the number of permutations will be equal to, it's usually given by 10 factorial divided by 4 factorial into 3 factorial into 3 factorial. So that is the meaning of what this particular equation 3. So equation number 3 gives the number of ways in which, okay, or it is called the weight factor. Usually it is called weight factor. It represents the number of ways. Okay, so you can remember this equation by either by this W or this particular W. Okay, weight factor or number of ways. So W stands for the weight factor, right? So this is nothing but the number of arrangements, actually, that is the thing. So now equation 3 represents the weight factor, or the number of ways in which such a distribution can occur. Now, what we have to find out, what we are supposed to find out, we are supposed to find out the most probable distribution. We are supposed to find out the most probable distribution set. Okay, therefore the most probable, most probable distribution set, what will be the characteristic, what will be the property of the most probable distribution set? Okay, so let me represent the most probable distribution set by the set NR star. I'm representing the set NR star as the most probable distribution set. We are interested in the most probable distribution set. Why? The reason is that, hope you remember, while discussing about microstates and the distributions in the very beginning of our statistical course, we have concluded that in the thermodynamic limit, the only probable distribution will be the most probable distribution. What does it mean, most probable distribution? What is the speciality? The most probable distribution would be that distribution which is having largest number of what? Microstates. Okay, or in other words, we had concluded that the macrostate having largest number of microstate will be the most probable microstate, and in the thermodynamic limit, the most probable microstate would be the the most probable macrostate would be the only probable macrostate of the system. Okay, so I'm using the same, I'm borrowing the same concept here. The most probable distribution set, which is labeled as NR star, would correspond to maximum number of W. Okay, maximization of W. Because what is W? W represents the number of ways in which such a distribution can occur. അപ്പോൾ W എന്ന് പറയുന്ന എന്താണ് ഡിസ്ട്രിബ്യൂഷൻ്റെ എണ്ണം, NRന് കറസ്പോണ്ടിങ് ആയിട്ടുള്ള നമ്പർ ഓഫ് ഡിസ്ട്രിബ്യൂഷൻസ് W കൊണ്ട് സൂചിപ്പിച്ചിരിക്കുന്നു. അപ്പോൾ ആ W ഏത് സാഹചര്യത്തിലാണോ മാക്സിമം ആവുക, ആ സാഹചര്യത്തിൽ ഏത് ഡിസ്ട്രിബ്യൂഷനാണോ നടക്കുന്നത്, ആ ഡിസ്ട്രിബ്യൂഷനെയാണ് നമ്മൾ എന്ത് പേര് വിളിക്കേണ്ടത്? മോസ്റ്റ് പ്രോബബിൾ ഡിസ്ട്രിബ്യൂഷൻ സെറ്റ് എന്ന് വിളിക്കേണ്ടി വരിക. ഓക്കെ, അപ്പോൾ നമുക്ക് പറയാൻ പറ്റും ദ മോസ്റ്റ് പ്രോബബിൾ ഡിസ്ട്രിബ്യൂഷൻ സെറ്റ് NR star will be most probable distribution set തിരിച്ചറിയാൻ വേണ്ടി നമ്മൾ സ്റ്റാർ ഇട്ടെന്നേ ഉള്ളൂ. Will be the one which makes the W of NR, W which is a function of NR, which means that W depends on the particular distribution set, W NR a maximum. അപ്പോൾ WNRനെ മാക്സിമൈസ് ചെയ്യുന്ന ഏതൊരു ഡിസ്ട്രിബ്യൂഷൻ സെറ്റ് ആണോ ആ ഡിസ്ട്രിബ്യൂഷൻ സെറ്റിനെയാണ് നമ്മൾ ഇത് വിളിക്കേണ്ടത് മോസ്റ്റ് പ്രോബബിൾ ഡിസ്ട്രിബ്യൂഷൻ സെറ്റ് എന്ന് വിളിക്കേണ്ടത്. ഓക്കെ, അപ്പോൾ നോക്കുക, ഇനി നമുക്കറിയാം. സോ ദിസ് ഈസ് ഓൺലി ദ കോൺസെപ്റ്റ് ഹിയർ. Now suppose you know that WNR has to be maximized. നമ്മൾ ഏതെങ്കിലും ഒരു ഫംഗ്ഷനെ മാക്സിമൈസ് ചെയ്യാൻ വേണ്ടി എന്താ ചെയ്യുക മാത്തമാറ്റിക്കലി? Mathematically we will define its the differential to be equal to 0. അല്ലേ, നമ്മൾ that we are employing everywhere, the maxima and minima test, or the condition for extremum. അല്ലേ, the first derivative should vanish എന്നാണ് പറയാറുള്ളത്. അപ്പോൾ ഇവിടെ നമ്മൾ എന്ത് ചെയ്യും? ടോട്ടൽ ഡിഫറൻഷ്യൽ ഓഫ് W should be 0 എന്നാണ് നമ്മൾ പറയേണ്ടത്. സോ ഡിഫറൻഷ്യൽ ഓഫ് W should be 0 എന്ന് പറയുന്നതിന് പകരം തീർച്ചയായിട്ടും തെർമോഡൈനാമിക് ലിമിറ്റിൽ ഈ N ഒക്കെ പറയുന്നത് N1, N2, N3 അല്ലെങ്കിൽ N ഒക്കെ പറയുന്നത് വളരെ വലിയ നമ്പറുകളായിരിക്കും. ഓക്കെ, സോ ഇൻ ദാറ്റ് കേസ് W വിൽ ബി എ വെരി ലാർജ് നമ്പർ. W എന്ന് പറഞ്ഞാൽ വളരെ വലിയൊരു നമ്പർ ആയിരിക്കും ഫോർ ആക്ച്വൽ സിസ്റ്റംസ് വെയർ ദ നമ്പർ ഓഫ് പാർട്ടിക്കിൾസ് ഈസ് ഓഫ് ദി ഓർഡർ ഓഫ് അവഗോഡ്രോ നമ്പർ. ദ W which is the number of ways in which a distribution set can occur will be quite large. It will be a very big number, right? അപ്പോൾ വലിയ നമ്പറുകളെ ഹാൻഡിൽ ചെയ്യുന്നതിനേക്കാളും എളുപ്പം നമുക്ക് എന്താണ്? ഇറ്റ് ഈസ് ഈസി ടു ഡീൽ വിത്ത് സ്മോൾ നമ്പേഴ്സ് വിത്തൗട്ട് ലോസിങ് എനി ഇൻഫർമേഷൻ. അതിനുവേണ്ടി നമ്മൾ എന്ത് ചെയ്യുന്നു പറഞ്ഞിരുന്നത് നിങ്ങൾ ഓർക്കുന്നുണ്ടാവും. ഒമേഗ എന്ന് പറയുന്ന നമ്പർ ഓഫ് മൈക്രോ സ്റ്റേറ്റ്സ് വളരെ വലുതായതുകൊണ്ടാണ് നമ്മൾ സാധാരണ ഞാൻ പറഞ്ഞിരുന്നു വി ആർ ടേക്കിംഗ് ലോഗ് ഓഫ് ഒമേഗ. ഇതിന് മുൻപത്തെ അപ്രോച്ച് നമ്പർ 1ലും നമ്മൾ ഡെറിവേഷൻ എടുത്തപ്പോൾ നമ്മൾ ഇൻസ്റ്റെഡ് ഓഫ് യൂസിങ് ഒമേഗ വി ഹാവ് ജസ്റ്റ് ടേക്കൺ log of omega. Okay, right? So why we are doing? Only because it's for mathematical simplicity. അപ്പോൾ WNR എന്ന് പറയുന്ന ഒരു വളരെ വലിയ നമ്പർ ആയതുകൊണ്ട് WNRനെ നേരിട്ട് മാക്സിമൈസ് ചെയ്യുന്നതിന് പകരം നമ്മൾ എന്താ ചെയ്യാന്ന് വെച്ചാൽ we will be taking logarithm of WNR. So we will be taking logarithm of WNR and then maximize that function log of W. Okay, and they are equivalent. Why they are equivalent? Because W is a number, log W will be a small number, that's all, which represents the value of W. Corresponding to every w value, there will be a log w value, which will be yet another number, but the number will be something like what do you say? I think I mentioned the word like, when you have a large file to send, a large digital file, a photograph or a video has to be sent over some social media, okay, or you have to upload it to YouTube. What we usually do is that we first compress the video, right? So a MB file will be just reduced to maybe a few KBs, okay. That is done by what is known as compressing the file, right? Okay, right. Either you can call it as compressing, or you can just zipping the file. And at the receiver end, the file can be what? Again, just you can just unzip the file, right? What do you say, to get back the original file. So I can say that in a way, taking logarithm of a large number is very similar to compressing a big file, big data file, right? Why? You can clearly understand. I don't know whether I don't remember whether I said to you or not, okay, earlier, that that log of 10. So 10, suppose that you have some numbers like 10, 100, okay, some 1000 or some 10,000. All these are some numbers that you have to handle. Okay, now once you take log of all these numbers, what happens? You take log of these numbers, you will see that log 10 will be reduced to 1, log 100 will be reduced to 2, log 1000 will be reduced to simply 3, log 10,000 will be reduced to some 4. Can you see that the same ratio is maintained here, 1, 2, 3, 4, etc. Okay, the number, okay, see that thing is the quantity is actually maintained here, with all the numbers between 10 and 100 will be now lying between 1 and 2. All the numbers between 100 and 1000 will be now again what? Lying between 2 and 3. Okay, so what has actually happened? The number 10 has been now reduced to or compressed to a number 1 on taking its logarithm. Number 100 has been reduced to a number 2 on taking the logarithm. Number 1000 is reduced to a number 3 on taking logarithm. So why do we take logarithm? Okay, in the physical concept, one of the very important reason why we take logarithm of certain quantities, okay, is to ease our calculation, because it is equivalent to compressing the number to a number that you can easily handle and number which you can easily comprehend. Okay, rather than talking about very big numbers. For example, you take logarithm of Avogadro number. Avogadro number is of the order of 10 raised to 23, right? So when you need not talk about 10 raised to 23, instead you can talk about what? 23, because 23 is a much easier number to handle compared to what? Avogadro number 10 raised to 23. Right? So the same manner, I am taking logarithm of w here. Always remember, we will be in many places we'll be taking logarithm of the quantity instead of taking the original quantity in statistical mechanics. Okay, and there are several other reasons for that. One reason is that, of course, calculation, algebra becomes simple when you take logarithm of the quantity, because the product becomes what? Sum, right? Or a quotient becomes what? Difference. All those, log a b will be equal to log a plus log b. Log a by b becomes what? Log a minus log b, right? So all those are a simplification of algebra, but the most important factor is that it is able to compress the number, and so that you can easily represent the number. So what I want to tell you here, I was just discussing something which is conceptual in all this derivation. Let me come back. So instead of maximizing w of nr, I'm going to maximize log of w. So log of w should be a maximum. Log of w should be a maximum for the set nr to be a most probable distribution. So I can write, of course, w of nr. We can omit it, okay, when it's understood. Now, let's see how to maximize log of w. So before maximizing log of w, let me find out what is the value of log of w from equation number 3. So you have equation number 3 with you. See, I'm taking from equation number 3. First, I'm taking log of w. I'm omitting the term of nr. Log of w. What will be log of w? See, equation number 3 is nothing but n factorial. Is not n factorial divided by n1 factorial into n2 factorial, etc. So it becomes what? Log a by b is log a minus log b. So it becomes log a means log of n factorial minus, what will be the thing? Okay, the denominator was n1 factorial into n2 factorial, etc. So it becomes a sum. So that is log n1 factorial, right, plus log n2 factorial plus etc. up to, okay, log say nr factorial. So this is what is going to happen. Now can you just simplify this one? It can be simplified like you can write this one log of n factorial, of course. So I'm trying to write the curly letter n, okay, minus all these terms put together I can take as a summation. Sum over r log of nr factorial. Log of nr factorial. Where this, what is this r? R value runs from 1, 2, 3, 4, etc. It goes. Right? Now, you know that in statistical mechanics, see, all these numbers are pretty big. Right? This n is the number of systems in the ensemble. N represents the number of systems in the ensemble. Okay, and you know that an ensemble represents all possible microstates that a system can access. And for a thermodynamic system where the number of particles is of the order of Avogadro number, of course the number of microstates will be pretty large. It will be much larger than the Avogadro number. So we can say that the number of systems in the ensemble, which represents the number of microstates that the system can access, will be of course a very big number, a number which is bigger than the Avogadro number actually. Okay, and this number n is made up of further numbers n1, n2, n3, etc. Because we have seen that this n1 plus n2 plus etc. up to some nr is giving you what? The total n. So we can say that since n is very large, the fractions or the parts which make up that n also would be what? Very large in the thermodynamic limit. So whenever there are large numbers and you take the logarithm of that one, its factorial, you know, you can just go for an approximation which is known as Stirling's approximation. So here I am using Stirling's approximation for each of the two terms, right? So what will be the Stirling's approximation expansion for the log n factorial? It will be of course log n factorial is equal to n log n minus n. That is the expansion for this log n factorial using Stirling's approximation. So minus what will be the, so of course sum over r is there, minus sum over r is there, then log nr factorial by the same token, okay, of Stirling's approximation expansion, nr log nr, okay, minus nr. So that will be the thing. Now can't you just open the bracket and rearrange this one? So this is approximately equal to, all these approximations are valid within the accuracy. So n log n minus sum over r nr log nr, okay, and this minus and that minus will become plus. It will be plus sum over r nr. And can't you see that this sum over r nr by equation number 2a, the constraint, it is nothing but the total number of systems in the ensemble. So that is nothing but n itself. So this is minus n and this plus sum over r nr is getting cancelled. So what you are left with is only the two things. Okay, so this is what you are getting. Now what I'm doing, see, let me take differential because we have to maximize log of w. So therefore taking differentials, what will be that? I'm taking delta of log w, that is the left side. That should be equal to, what will be delta of, you have to take delta of each of the two terms on the right side. There are only two terms that is left on the right side. You know, what will be delta of n log n? What is n? N is the total number of systems in the ensemble, which is a constant. So n is a constant, remember. Total number of systems in the ensemble is a constant. But what can vary? This value of n1, n2, n3, nr can vary. Because nr, the set nr depends on what? Okay, the way in which energy is distributed. So the set nr can vary, means the value of n1, n2, etc. can vary, but total n is a constant. So since n is a constant, the differential of the first term will be vanishing, that is equal to 0. Okay, minus, so in the second term, you can see there are nr and log nr. It is just like a function, u into v form. So I have to take function of function rule for differentiation. So that will be equal to, let me take, right, like sum over r, that is the term there. So first term I am taking nr, so it is delta nr into log nr. So I have taken the differential of the first term with the second term. Then plus will become minus, okay, u dv plus v du. That's what I am writing. Minus, what is that? Sum over r. Of course, that sum over r term is there. nr into differential of log nr. What will be differential of log nr? It should be equal to differential of log x is 1 by x, okay, into dx. So I have to write into delta nr. So instead of x, sorry, I have to write what? nr, 1 by nr. Okay, so this 1 by nr, this nr and this nr will be getting cancelled. So what is left out is sum over r delta nr. Now you can see that the sum over r and delta nr are common for the first and second term. So I can rewrite this one as equal to minus sum over r. So what is remaining? I can write 1 plus the 1 corresponds to this particular 1 minus is already taken out. So what is there? 1 plus log nr delta nr. I am writing delta nr to the end. So this is actually, let me call this equation as equation number 4. So what is this equation number 4? Equation number 4 represents the differential of log w. See, let's pause a second and look back. What was this w? W was the number of ways in which a distribution set nr can occur. Okay, and we were trying to maximize w in order to find out the most probable distribution set. And instead of maximizing w, we went on maximizing what? Log of w, because w is a pretty large number. And finally we have reached this equation delta of log w equal to some equation number 4. Now what is the condition? For w to be maximum, as we know, okay, the maxima minima condition, the differential should be equal to 0. So therefore, for w to be maximum, for w to be maximum or log w to be maximum, when w is maximum, correspondingly log w also will be maximum, that we know. So I can say delta of log of w given by equation number 4 should be equal to what? 0. Okay, that is also we can say this is one condition that you have to keep in mind. Okay, delta of log w should be equal to 0. Not only that, let me add a page here. Not only that, see, for the set nr, for also, just a moment. Also, okay, for the set, there are some constraints. No, we have to take into account the constraint. For the set nr, to be maximum, for the set nr to be maximum, okay, the variation in it, what is represented by delta nr, the variation in it represented by delta nr should satisfy, the variation in it should satisfy the conditions, the variation also should satisfy the conditions 2a and 2b. 2a and 2b. Hope you remember what is 2a and 2b. So 2a was sum over r nr is equal to n, that is 2a. Okay, and what is 2b? That is sum over r nr er is equal to total energy E. Okay, no, that is 2b. So the variation in delta nr, which is represented by delta nr, should also satisfy these constraint equations. Okay, that is, you take delta of equation 2a and 2b, take differential of equation 2a and 2b, that's all. So what we on taking differential of equation 2a, left side will be sum over r delta of nr is equal to, what will be the right side? Take differential on the right side. What is differential of n? N is a constant, so differential of n is equal to 0. We call this one as say 5, say 5a. Okay, and similarly you take differential on both sides of 2b. So left side you will get sum over r. Okay, what will be the thing? nr and er. Should we use the product rule or not? Are nr and er both variables, or only one is variable? So we will see that out of nr and er, actually in the present problem, nr is variable, but er should be treated as what? Constant. I will explain why. So I'm writing it as what? I'm writing er as a constant. So it is not affected by taking differential. So only what is left out is delta nr, and on the right side taking differential of total energy shared by the members of the ensemble, that is equal to 0. So let me say that this is 5b. Okay, now let me explain. I think you are able to understand. I don't know whether you remember, I had mentioned it earlier somewhere in some video, that what is ER representing? ER representing the different the energy values of the system, right? Or the value of the energy possessed by different levels of the system. For example, suppose you take a system, say our system be the simplest one, hydrogen atom. Okay, so say for hydrogen atom, that's our system. Okay, now you know in the case of hydrogen atom, the energy levels are actually what? The energy level values are fixed up. You know, the ground state energy E1 is equal to minus 13.6 electron volt. That's the value of E1. So this is corresponding to N1. Now E2 is equal to what? Minus 13.6 divided by 4 n square. Okay, so n square to n equal to is 4. So it will be some minus 3.5, minus 3.54 electron volts, say. And E3 will be equal to corresponding to N3, corresponding to the third level. This is for the corresponding to the first level. This is corresponding to second level. So that will be equal to some minus 1.8. Okay, 1.81 electron volt. So you can see that for a system like hydrogen, the value of E1, E2, E3 is what? Fixed. That is decided by the the system itself, right? So the value of the energy levels are characteristic of the particular system. It will not change with the distribution. What only will be getting changed is the number of particles in each of these levels or states will be getting different. Okay, so when the number of the number distribution of particles in each of the state is different, we call it as different distributions. So remember, ER is unique. ER, so the value of ER is unique. That is what you have to always remember. ER is not a variable for a particular system. ER is unique for every system. ER is unique for every system. It's a characteristic of the system that we are considering. So that is the reason why that I have taken ER to be a constant and only NR is variable. NR is the number of particles in each of the states there, right? So remember, sum over R always denotes sum over all states. It's not sum over all levels. Okay, so if the levels are degenerate, you have to consider each of the state corresponding to a particular level separately, and all the summation in statistical ensembles are sum over states. That's why you call it as a partition function is the sum over states, just and summing. Okay, sum over the states, not levels. Okay, so remember, because a level can be degenerate, so which can have a large number of states. What you have to ultimately count is the sum over all states. Okay, accessible is micro states. States come from accessible micro states. So this is equation number 5a and 5b. Now our problem is almost coming to an end. Okay, so what we are where we have finally reached, we have finally reached the two conditions. One is equation number 4. What is equation number 4? That I have to maximize log of W NR. Okay, log of W corresponding to a set NR has to be maximized. For that, delta of log W should be equal to 0. This one we have called as equation number 4. And this log W എന്ന് പറയുന്ന ഫംഗ്ഷനെ മാക്സിമൈസ് ചെയ്യപ്പെടണം. അതിനുവേണ്ടി അതിന്റെ ഡിഫറൻഷ്യൽ 0 ആയിരിക്കണമെന്ന് നമ്മൾ ഡിമാൻഡ് ചെയ്യുന്നു. പക്ഷേ ഈ ഫംഗ്ഷനെ വെറുതെ അങ്ങോട്ട് മാക്സിമൈസ് ചെയ്താൽ പോരാ. ഈ ഫംഗ്ഷൻ മാക്സിമൈസ് ചെയ്യുമ്പോൾ that should be satisfying some constraint equations 2a and 2b. 2a and 2b നമ്മൾ എന്ത് ചെയ്യുന്നു? ഡെൽറ്റ ഓഫ് ചേഞ്ച് ഇൻ എൻ ആറിന്റെ ടേംസിലേക്ക് മാറ്റി എഴുതിയതാണ് 5a and 5b. ഓക്കെ, സോ equation number 4 should be satisfied along with equations 5a and 5b or equation 2a and 2b. അപ്പം ചില കൺസ്ട്രെയിൻസ് സാറ്റിസ്ഫൈ ചെയ്തുകൊണ്ട് W എന്ന് പറയുന്ന ഈ ഫംഗ്ഷൻ എന്താവണം? മാക്സിമൈസ്ഡ് ആവണം. അങ്ങനെ കൺസ്ട്രെയിൻസ് സാറ്റിസ്ഫൈ ചെയ്തുകൊണ്ട് W മാക്സിമൈസ് ചെയ്യുന്നത് ഏത് സെറ്റ് ഓഫ് NR വാല്യൂവിനാണോ ആ സെറ്റ് ഓഫ് NR വാല്യൂവിനെ വിളിക്കുന്ന പേരാണ് മോസ്റ്റ് പ്രോബബിൾ ഡിസ്ട്രിബ്യൂഷൻ സെറ്റ്. ഓക്കെ, ഇങ്ങനെ ഒരു കൺസ്ട്രെയിൻറ്റുകൾ ഉൾപ്പെട്ട മാക്സിമൈസേഷൻ കണ്ടീഷൻ പ്രോബ്ലംസ് സോൾവ് ചെയ്യാൻ വേണ്ടി നമുക്ക് മാത്സിൽ ഒരു നല്ല മെത്തേഡ് ലഗ്രാഞ്ച് who is regarded as one of the mathematical genius has developed. ആ മെത്തേഡിന്റെ പേരാണ് that is known as the Lagrange's method of undetermined multipliers. Lagrange's method of undetermined കണ്ടുപിടിക്കപ്പെടാത്ത എന്നുള്ളത്. ഓക്കെ, തുടക്കത്തിൽ അതെന്താണെന്ന് നമ്മൾ എടുക്കുന്നില്ല, രണ്ട് കോൺസ്റ്റന്റ് എടുക്കുന്നു. അൺഡിറ്റർമിൻഡ് മൾട്ടിപ്ലയേഴ്സ് ഇത് എവിടെയാണ് ഉപയോഗിക്കേണ്ടത് എന്നുള്ള അടുത്ത വീഡിയോയിൽ ഞാൻ വിശദമായിട്ട് പറയുന്നുണ്ട്. ഇപ്പോൾ തന്നെ നിങ്ങൾക്ക് മനസ്സിലാവും എന്താണ് ഒരു ഫംഗ്ഷനെ മാക്സിമൈസ് ചെയ്യണം. ഓക്കെ, ആ ഫംഗ്ഷന് പക്ഷേ ചില കൺസ്ട്രെയിൻറ്റുകൾ ഒബേ ചെയ്തേ മതിയാവുള്ളൂ. അപ്പോൾ കൺസ്ട്രെയിൻറ്റുകൾക്കുള്ളിൽ നിന്നുകൊണ്ട് ഏതെങ്കിലും ഒരു ഫംഗ്ഷനെ മാക്സിമൈസ് ചെയ്യാൻ വേണ്ടിയിട്ടുള്ള ഒരു മാത്തമാറ്റിക്കൽ ടെക്നിക്കാണ് ലഗ്രാഞ്ച് സജസ്റ്റ് ചെയ്ത ലഗ്രാഞ്ചസ് മെത്തേഡ് ഓഫ് അൺഡിറ്റർമിൻഡ് മൾട്ടിപ്ലയേഴ്സ്. ഇത് നമ്മൾ അടുത്ത വീഡിയോയിൽ ഞാൻ ഡിസ്ക്രൈബ് ചെയ്തിട്ടുള്ളത് എങ്ങനെ ലഗ്രാഞ്ചസ് മെത്തേഡ് ഓഫ് അൺഡിറ്റർമിൻഡ് മൾട്ടിപ്ലയേഴ്സ് ഉപയോഗിച്ചുകൊണ്ട് ലോഗ് ഡബ്ല്യുവിനെ എങ്ങനെ മാക്സിമൈസ് ചെയ്യാം എന്നുള്ള കാര്യം ഡിസ്കസ് ചെയ്തിട്ടുണ്ട്. ആൻഡ് അറ്റ് ദ എൻഡ് ഓഫ് ദ ഡിസ്കഷൻ വി ആർ ഏബിൾ ടു ഗെറ്റ് ബാക്ക് ദ ഇക്വേഷൻ PR which denotes what is known as what the Boltzmann distribution PR is equal to e raised to minus beta ER. ഇത് നമുക്ക് വളരെ ഫെമിലിയർ ആയിട്ടുള്ള ഇക്വേഷൻ ആണ്. ഓൾറെഡി നമ്മൾ ഫസ്റ്റ് അപ്രോച്ചിൽ ഡിറൈവ് ചെയ്താണ്. ഡിവൈഡഡ് ബൈ വാട്ട്? സം ഓവർ ആർ e raised to minus beta ER, and the denominator you know that this is nothing but the canonical partition function. അപ്പോൾ നിങ്ങൾ ഓക്കെ ഇതുമായി കൂട്ടിച്ചേർത്തുകൊണ്ട് അടുത്ത വീഡിയോയും കൂടി കാണുക. So whatever is missing, okay, try to just read okay your notes or whatever study material that you have. Okay, I hope that it will help. Thank you.